Hello and welcome to the fourth video of the playlist. In this video, we will see on how to create the heating configuration file and what are the significant fields in the heating tab of a CMD simulation protocol. Without further ado, we will move on to the main window. As you can see, this is the main window of the NMD Automata and this is the CMD interface, a subsequent window of the same application. We have kept it modularized as mentioned earlier because we want to check the errors if there are any. We want to log them. We want to troubleshoot these errors through the CMD window, and subsequently if there are any further errors in the configuration file, we can change them in this particular tab or the subsequent tabs of the NMD simulation stages. Okay, so with moving forward, as you can see, this is the second form of NMD Automata, and before we start working on this tab, we first have to set the directory. Mentioned earlier in the video, we have said that we have to set a directory, and I have kept a directory as test. We have set it, and we will move on to the next tab, which is the minimization tab, and then from here to the heating. So I have explained set directory and minimization tab in the earlier video. Please check it if you haven't. And in this video we will be explaining the heating and the equilibration tabs, both of them, in this video, and we will make sure that you learn much more about these two tabs other than just reading about it and just using this application. So coming forward to the heating tab, first let us learn and let us enlighten ourselves to know the significance of heating tab. So in this stage of CMD simulation, it corresponds to the process where temperature of the biomolecular system is brought to nearly 300 Kelvin. This temperature correlates to an average temperature where most of the proteins are physiologically active. So in this phase, the system is gradually increased from 0 to 300 Kelvin, and at each time step, the temperature will be increased by 0.001 Kelvin. In order to gradually increase the temperature, various temperature reassignment parameters have been set as field parameters in this form, and it needs to be specified in the configuration file. So moving forward from here, now that we have learned the significance of heating tab, we will check out the most important fields in this tab. Mentioned in the earlier videos, I have explained all the other significance of these fields, and we will move on to this field called as time step and full electrostatic frequency. These two fields are much more important in this particular section as they have been introduced newly in this section, and to cut the time short, we are not going to explain everything again from the top. We will just keep our heads on these particular sections. So the first is the time step section. We have kept the default value as 1, and users are advised to not change the time step value in this stage. It will be showcased as 1 when you will be using it from your end, and to maintain a biological relevance, we have to keep the time step as 1. Next is the full electrostatic frequency. This value is set to 4 femtosecond, and the value 4 indicates that the full electrostatic evaluation will be conducted after every 4 femtoseconds. In the output block, there are certain changes comparing to the minimization tab. The names of the files have been changed based on which stage you are working. So it has been kept as complex heat restart, and complex heat.dcd file. The other things are kept unchanged, and the next most important part of this tab is the MD protocol block, and this is the heart of this configuration file and eventually the heating process. So the MD protocol block starts from seed to reassign hold. This is the whole thing, this is the whole section we are talking about. So starting from seed, it is to specify one very random number that will be used to assign an initial velocity or initial velocities. The next field is the number of steps. We have kept it as 3 lakhs over here. Specifies the number of times for running the simulation, and the heating simulation is needed to be run for 300 picoseconds. Therefore, we have kept this value. Only if the time step, as we have mentioned earlier, is kept as 1. Over here you can see that it has been kept 1, so the calculation turns out to be 300 picoseconds. So I will of course mention about the theoretical part of how to calculate it. I will be there in a few minutes, but before that we need to learn about these fields. Therefore, the total simulation time will be 300 picoseconds as mentioned earlier. And the field initial temperature is kept as 0. Like mentioned during the significance of the heating tab, we learned that we have to gradually increase the temperature from 0 to 300 Kelvin. So we have kept initial temperature as 0, and the holding temperature, where we will be holding the biomolecular system, is 300. Also mentioned earlier that we have said that it has the temperature will be increased gradually by a value of 0.001 Kelvin. So this reassign increment does that same work. So the next thing that we need to learn is the reassign frequency. Here the setting up of the value to 1 means the temperature is to be increased after every 1 femtosecond. Okay, like mentioned earlier, we need to learn about the theoretical aspect of how to calculate it. So I'll briefly give you the theoretical formula for this calculation, which is total simulation time equal to number of steps into time step. So number of steps is 3 lakhs and the time step given was 1 femtosecond. So if we calculate it and simplify it to a integer number, we will get as 300 picoseconds. Also the cell basis vectors have been set up, all of them, like you can see. Cell basis vector 1 with x coordinate, 2 with y coordinate, 3 with z coordinate, and cell origin values have been populated as well. Now we will be creating the heating configuration file. So when we click on this button, create heating configuration file, we will be showed with a pop-up block telling us to save the configuration file. So the default value for this file name will be the default name for this file. It will be heating.conf or heating.configuration. We can change the values. This is also an advice to the users that when you are running multiple simulation tasks, you should change the names of the output files. So we will save it, and you will be shown that your simulation parameters are saved to configuration file. And when we go to this next tab, next pop-up message that gives us is heating file generated successfully. So we'll click on OK. That is done, and as you can see in the CMD interface, you are given an update that your simulation parameters are saved and the file has been generated successfully. So next we will move on to the subsequent equilibration stage. Over here, the next stage, which is the equilibration stage or step of the CMD protocol, just like previously mentioned, we don't have to do anything on the input parameters. Everything has been given by default with the names. Like mentioned, if you want to change it, you can change it, keeping in mind that the names correspond to the output name in the previous tab. So what I mean by that is, when you are looking into the output name for this section, which is complex heat, equilibration tab should also have complex heat as a coordinate file name, as a velocity file name, and an extended system file name, with of course changes in the extension. Although we have kept it as default over here for the ease of the users, but we advise you to keep in mind, if you change it, then change the file names as well for the subsequent tabs. Again, we don't need to check on parameter paratype charm, parameter files are all given over here. All the values have been carried forward from the first minimization tab. But what are the most important things that we need to learn from this tab, and subsequently how to create the configuration file from this tab, are to be mentioned right now. So first let us learn about the equilibration tab significance. We need to first elucidate on this particular theoretical aspect. The final goal of a simulation task is to sample the structural states of the biomolecular system at equilibrium. So it is intended in this stage to achieve the equilibrium for final data collection in the subsequent production stage, in this stage. Both the stages are quite similar in the form filling point of view, and with minute changes in the parameters that makes them unique in themselves. So there are certain things that are here in this tab, equilibration tab, and certain value parameters in the production tab. They have a little change in them, but we will look into it further. Now, coming to the major aspects of this tab is the Langevin dynamics, Langevin damping, Langevin temperature, hydrogen, use group pressure, flexible cell, constant area, and up to Langevin piston temperature. So what are the significances of these particular fields in this tab? We will move on to them one by one. So, and also, of course, before I forget to mention them, there has been introduction to the rescale frequency, rescale temperature, where the values are quite similar to the previous heating tab, but we have changed the name. There was reassign and now this is rescale. We have changed the name, and what is the significance of these name changings? We will look into that. Give me a moment. So before I move further, in the temperature control block, so this is the temperature control block, the Langevin temperature, Langevin hydrogen use. These are the temperature control block, and the fields mentioned earlier are the pressure control block. So in the I'm sorry. So we'll get onto it right away. So in the temperature control block, this starts from the Langevin dynamics. We kept it as on. We will enable it as on. Then coming to the dynamics, the damping section. In the field Langevin damping, the value is set to 1 by default, which is the damping coefficient gamma to 1 picosecond to the power minus 1. The value less than 1 might reflect weaker coupling to the heat bath, while value greater than 5 in this field might mean stronger coupling. The default value is 1, and which is the most optimal value for maintaining the temperature of biological interest. Then is the Langevin temperature field, and is meant to set the target temperature of the simulated thermostat. So that is, our target is 300 like mentioned earlier, so we will keep it as 300. The default value of 300 in this field means that the biomolecular system will be regulated around 300 Kelvin during the equilibration process. Then comes the Langevin piston pressure control method. The first field is the use group pressure. It enables or instructs NAMD to use the group based contribution for pressure calculations rather than single atoms. It is mandatory to use group pressure utility when rigid bonds are activated for all atoms including hydrogens in the constraints setting. Using the value no in the field use flexible cell, like here, means that the shape of the simulation box will not change. It will be assumed that the pressure calculations will be isotropic, that is, the box can either expand or contract equally in all directions. Isotropic pressure calculation are recommended when the system is isotropic. The simulation of the globular protein in a solution is a typical example of isotropic system, just for the information. And there are many other examples for a globular protein. You can look into them later, but this is one of the typical examples that we thought of mentioning in the video. In short, the CMD protocol described in NMD Automator best suits the biomolecular systems where globular proteins are solvated. So this is the main factor, the prime factor that we are talking about. Okay, so initially the value no in the use constant area, like here, is related to the choice made in the field use flexible cell. Setting it to no would mean that the area can change. Using yes value in the use constant area would be more appropriate in membrane based simulations. The remaining fields in the block pertain to the Langevin barostat that maintains constant pressure, like Langevin piston target, piston period, piston decay, and piston temperature. Here NMD simulates a piston variable that couples to volume change and thus control the pressure in the system. In the field Langevin piston, the default value is kept as on, indicating that enabling the usage of Langevin piston method to simulate the artificial barostat. The default value is for Langevin piston target is kept as 1.01325. Now why this big value is kept after the decimal? In the field Langevin piston target, it is to basically target the pressure value in bars. The value is kept is in bar and it is equivalent to 1 atmospheric pressure. Thus the value. During the simulation, the system volume is set to adjust dynamically to maintain the pressure of 1 atmospheric pressure. And setting the value for Langevin piston period to 100 means that oscillation period of 100 femtoseconds is set for the simulated piston. This value decides how fast the system will respond to the fluctuation in pressure in the simulation. 100 is a moderate value suitable for most of the solvated globular biomolecular systems. The field Langevin piston decay, next field, which kept as 50 as a default, expects the value of the damping coefficient, which can be alternatively referred to as friction coefficient in femtosecond time scale. This value controls the decay time of the piston oscillation. The final field in this block is the Langevin piston temperature, which connects the thermal bath temperature in the thermostat setting. This value must match the simulation temperature in default. So we have kept Langevin temperature 300. We have to keep the piston temperature as 300 as well, 300 Kelvin. So the take-home message in this tab is that the default values in temperature and pressure control are well calibrated for a typical biomolecular system. So we have calibrated it based on a detailed experimentation for any biomolecular system. If the user, like I mentioned earlier, decides to change the setting, then corresponding lines are needed to be updated using this block, which is user defined simulation parameters. So we can think of adding extra parameters into the configuration file, and if you as user wants to change something, wants to add something, add constraints, fixed atom constraints, then you can put it in this text box. So now we will create the equilibration configuration file. It is quite similar to the previous step. A pop-up will show up telling us to save the configuration file, and a default file name will be shown, which is equilibration.conf. I'll keep the file name as it is. I am not changing it. but it is again advised to the users, if you want to change it accordingly, but keep in mind that you keep a tab on what changes you are making to the file name, to the configuration file, to the output file names, everything. And when we save it, the same pop-up message shows that your simulation parameters are saved, and the next pop-up message shows equilibration file generated successfully. The same thing will be shown in this CMD interface as well. So that's it, my friends. For now we'll keep the video short for you to cope up with the pace, so that you can understand each tabs one by one and do not have to hurry with learning. And keep in mind that when we are using this NAMD automator, we need to make sure that as less as possible, we need to keep the errors as less as possible. So thank you, keep learning, and we will meet in the next video.